Hey, what's up everybody? I'm Sam Deiter, one of the senior technical writers here at Epic, and today I'm with Ryan Brucks, one of our senior, I'm going to call him a wizard, graphics wizard maybe. And today we are going to go over how to set up and use the custom material node, which allows you to write custom HLSL code inside of the material editor, and some of the ins and outs that you need to understand when you use that particular node. Now, before we jump really far into this session, keep in mind that the custom node, the HLSL node that we're talking about, this is like a next level. You really need to use this to do something that you just cannot get to work inside of the editor, something like the material editor, I'm sorry, something like a for loop or something with like, I don't know, distance fields or something like that, something that the material editor doesn't do right out of the box. But we see this question asked a lot on the forum, so that's why we wanted to cover it. About 99% of everything you're ever going to want to do with the material can be done with the built-in material nodes. So for a quick outline, what we're going to be doing today is we're going to go over what the custom node is, what you can use it for. Ryan's going to show you some awesome things that he has done with it, including some metaballs, and how you can do some debugging to figure out if your math is correct. So with that little intro out of the way, let's go ahead and let's get started. So I'm going to steal the mouse really quick. And the first thing I want to show you guys is this page right here. So this is the custom, and my mouse is going a little crazy on me here. This is the custom expressions reference page. This is just gives you a breakdown of the custom material node itself, how you activate it, and then what some of the parameters are, as well as the warnings for using this particular node. If you do end up using this node in your project, don't let these warnings down here at the bottom of the page scare you. Basically what they're saying is if you write something in this node and you go to release it into your project, you run the risk of the code not acting as performant as it could. That's because under the hood, the shader editor does a lot of things called folding, which will fold a bunch of instructions down to make it one single instruction, so it does automatic optimization. When the material editor comes to the custom node, what basically happens is it just looks at the custom node and just spits out that information without doing any type of internal optimization on it. So you need to make sure that if you're going to use this, that your code is running as performant as possible and that you've profiled it using something like NVIDIA Performance HUD or Microsoft's Pix or some of the other performance debugging tools that are out there, so you can see what registry addresses are being used and how expensive that actual shader or that actual part of your shader is going to cost in the long run. Let me see, and so that's it from here. This page right here, again, is purely for reference, and you're going to find a lot of useful information on the custom node itself. Even though there's not a lot of info on this page, the reason for that is there's so much stuff that the custom node can allow you to do that we just wanted to show you guys where it is and what it can do. But there's literally anything that you want to be able to do with it, you can do with it. And let me see, what else do we got here? So one of the reasons that we would want to use the custom node instead of writing stuff out or using the material nodes, I'm sorry, to make something is, again, if you want to do something complicated like a for loop. And let me see what I've got. 1 second here. All right, I'm going to click to one of your pages. So, for example, here's some code that Ryan wrote for the Metaballs example. And you see stuff like float 3, camera vector, or current position, or normal. These are all values that you could actually have these made inside of the material editor using the built-in material nodes. But when you get to things like this, when we want to do a while loop, that is not something that you currently have the ability to do inside of the editor, and that's why we would want to use the custom node. Ryan, you got anything that you would like to add to this?
That's a pretty good introduction, I think. Yeah, it's mostly right now there to fill the gap that we have with the editor shader extensibility, which right now there's not a super great path for writing your own shader code that modifies the entire engine without a little bit of know-how behind all that stuff. So the custom node is just a way to write simple HLSL code for people who don't really know the material editor or like Sam said, or if you have some operations that you need to do that are not either exposed or not possible. And then another possible use that some people are finding is to access things deep in the engine that haven't yet been exposed to artists. And that's something that effects artists are starting to do a lot more as they're getting really tweaky for cinema quality cinematics. So little things like accessing the camera depth of blur amount so they can fake their own depth of field in the particles and stuff like that. You can all access that, and we'll get into a little bit of how to do that as we kind of get through here a little bit. Did you have any other stuff before we jump in?
The last thing that I wanted to cover is what the custom node isn't going to do for you, because I don't want to give the illusion to anybody that, oh, well, I know HLSL, so I can just go ahead and forget the shader editor and just start typing everything up in here. And that's not what this node is designed to do. Again, like I said in the beginning, 99.999% of the time, all you're going to need to use is either the built-in material nodes or material functions that come with the Unreal Engine. This is not going to spit out optimized code. You're going to have to optimize it yourself. And it's not a magic, like, one-stop solution to any type of shader issues that you might be having or material that you just can't build. This will help you build that material, but it's not a magic solution, and you have to use it with a little bit of caution because it could end up giving you some very, very weird debug error that could take you weeks to figure out that you accidentally forgot a period somewhere in your shader. So just user beware. But with that out of the way, we're going to go ahead and jump right into the awesomeness of it. So I'm going to go ahead and hand it back over to Ryan to take over for us.
All right, so a couple preliminary notes. Sam mentioned the debugging. That is a good point. There is one engine change that most people who are going to do custom node writing should make right away, and that is to go to, you have a engine config directory, and you should have a file called console-variables.ini. If you scroll down a little bit, not very far at all, you'll see that there's this line, shader development mode equals 1. Notice it hints that you can uncomment things in here to get more detailed debugging. We've uncommented that here. It'll make the shader compiler take a little more time to figure out what's wrong, but it'll be a lifesaver when you're writing code. Like we just had this problem here just before the stream, pasting in one of my old shaders, had a syntax error and had to enable it to help find the line. So it'll basically tell you what line and a basic idea of what your error is. So
yeah, if you get an error now, it's just going to tell you you have an undeclared identifier, you're using a vector. It's not actually going to tell you what line number that comes on.
It won't even say that. It'll just say compile error if you don't enable this.
Yeah.
It most likely won't say anything.
So this is very important to turn on if you want to actually get some useful debug information, or if you like to fly by your seat of your pants, you could leave it off, I guess.
Now this other one, dump shader debug info. This is what you'll have to do if you end up needing to debug your custom node on a target platform. For example, PlayStation 4. And this is a real-world example where I had written the parallax occlusion mapping node is a custom node, and when we started using it in Paragon, the first time I went to test it out, of course, there was a compile error. I actually had to get a little bit of assistance from one of our rendering guys who told me to enable this and look through a few places, and we discovered that it was because I had uninitialized a integer variable, which basically means declaring it without saying it equals something right away. That worked fine on PCs and OpenGL on PC, but it failed on the PS4, so this will eat up a lot of memory though if you leave it on long term, because it's actually dumping all of the shaders for all the platforms. But you can actually go and read the actual, for example, HLSL code for different platforms, and sometimes it's quite different. So again, close that down. We've already enabled that, like I said. So I've got a couple of material examples that I can show you guys here today. And some of these things have been asked on the forums quite a bit. So I don't know how many of you guys have seen the ProtoStar video. I don't know, do you want to show that real quick?
We've got it actually queued up. If you kicked over to the Google over there, and then click over to the next one. There we go. Just click play and hit full screen.
All right, so this is the Metaballs effect at the beginning of this video, which was using a version of ray trace distance fields that is similar to our volumetric decal feature. But of course, since we were targeting a mobile platform for this, it had to be fairly efficient compared to what you would normally do.
And this does run at a, what was it? I think it runs at, is it 30 or 60? I mean, I've seen this.
It was at 30 FPS, but yeah, I mean, it was on a phone.
I've seen it on an actual Samsung smartphone, like played this in my hand with the insane resolution. It looks absolutely amazing. If
Plus
you're ever
there's-
at one of our shows, you should definitely swing by and check it out. Absolutely amazing tech, especially that it's running on a phone. That's the craziest part to me about it.
With planar reflections. So in this scene here where you see the reflections on the marble floor, that was actually something one of our programmers out in Seattle, Ryan Vance, did for this build. It's actually re-rendering all of those meshes and getting a accurate planar reflection.
This is awesome looking. Love the real-time reflections. Looks amazing.
We did have a little bit of issues getting the reflections of this sun material to match, but I won't go too much into that. That was more a running out of time thing.
The water looks cool.
And of course, Shane Cottle's awesome space finale.
Love the debris belt on the
Yeah,
ringed planet.
You did a nice job with that. Alright, I guess that's
Yep, that's it.
That's pretty much that. So I have a couple different versions of the Metaballs here, starting with a very simplified version, which is pretty much just doing silhouette rather than all of the refraction and everything. And I just wanted to kind of show you guys the basic gist of how it's assembled. So you'll notice that even though we see these different meshes here, this is actually a single cube. If I were to get rid of the material, it's just a regular box. There's no spheres or anything in there. So this is a material that's using, pardon me, using the
There we go.
using the custom node to basically ray march through the distance fields. And obviously we had to keep things pretty simple for mobile and keeping the step count low and everything. So I'll give you guys an idea. So for right now, this is this whole shader for this distance field function. So you see we have one shader, which is the main ray marching function. Bring that out. And I'll bring up this code in Notepad in a second so you guys can actually see it a little bit. Don't worry about trying to squint your eyes. So basically we have one node that does the ray marching, and it's actually, you notice here the top pin is called custom 0, and that's another custom function. So that's one of the things that is a little bit tricky for people to figure out when they're first starting this stuff out, is calling multiple functions across each other. And the engine has a little bit of a hard time handling that properly unless you kind of assist it and help it do it in the right order. So notice here that we want to call this function with this function. So to make sure that the engine includes the top function first, we actually chained it into the second function. And that just causes the compiler to order these so that this one is first. Otherwise, there's a potential chance that the engine can put this one into the shader first, and you try to call this one. And what's happening under the hood is these get called custom expression 0, 1, 2, 3, etc. Under the hood based on what order the engine thinks it needs them. So I'm going to go ahead and pull up the code for that over here. You'll notice this is the Metaballs shader. Basically, it starts out giving a camera vector that we want to trace along, initializes the position as the current world position, sets a few variables like the step size, the number of steps, and these are just initialized variables to 0 so they can be used in the loop. And then we do a loop through all of the steps, which we defined here to be 16 steps. And in each one, we're actually calling our other function. And there's a good reason why we would want to do that as opposed to putting it all in line. So we're calling this function here, and it's passing in the parameters, and it's going to get a result and put it into this variable, rather than having to have all of these lines that are in this function in the shader. And that gets even more important as you start doing things later on. Like
basically like nesting
Exactly.
something inside of something else, but instead of having just a giant thing to read down, you have separated the nesting into
Right.
custom 0 and custom 1.
So it makes it so that we can, for example, sample a normal map of our distance field by taking 3 offset samples. Notice we have an offset on the red channel, green channel, and blue channel. And by doing that, it lets us basically calculate a normal without having to have every single line from this function 3 times, which if this was expanded out to this function for all 3 samples, it would take up this whole page probably. So keep that in mind if you want to call functions within other functions that you want to kind of nest them like that. So now that you've seen a little bit of how something like that might be structured, I'm just going to go and point out a few things about what's going on here, and then kind of break things down a little bit to simpler problems, because I think people probably see something like that and they think, oh man, it looks complicated. So we have a few things going on here. You'll notice that I'm only taking 16 steps, so at certain angles we kind of see holes in the trace. Increasing the threshold for the ray tracer will help solve that. So you'll notice if I have a small threshold, we start to not be able to trace. For the mobile demo, we had to have a fairly low precision threshold, obviously, to keep the step count low. The other thing is this variable k, which is what's affecting how smooth the transition between the metaballs is. And that's actually something called a smooth min operation, as opposed to just combining the balls with a minimum. It's kind of lerping them together, and this is maybe something you'd see for a lava lamp or some sort of cellular animation. And for the actual four positions, or sorry, spheres, we have three spheres in this shader right now. Two of them are simple, just vector parameters, and we can actually move them around by doing this. And you'll notice I have this other, the third sphere is on a rotate about axis, and that's simply so that it's always moving, so I have a way to view the material in different angles without constantly moving my camera around. So that's something I might do in debug stages, is add in this extra rotate about axis. Where you see here I'm telling it what pivot to rotate, giving it a speed, and I can give it a start offset just in case the speed is 0. And I pass those three spheres in as positions, and it's able to then pass the spheres to this function and get the results back. So now that I've shown how that is kind of organized, I'm just going to back up a little bit and show, for example, what exactly is something like this smooth min, and how does that function. So I'm going to go ahead and close this material real quick. We'll come back to it in a little bit. And I'm going to put on a different material here real quick. I've got this folder graphing.
This is actually pretty cool.
So this is kind of how I tend to debug and kind of model math functions in the editor.
If you guys have seen this stuff, it might look a little familiar. I do believe a lot of this is in the Math Hall content example.
Yes, exactly. So that's where this stuff was made for. So this is basically a material function that lets you debug what the math of something is. There we go. Excuse me 1 second, I want to set this preview up to be a little bit more useful for our purposes here. Alright, so I'm going to hide this stuff for now. That's what we're going to be building. So this function, plot function on graph, it basically takes a function over a certain range and tells you what the value of it is. And the way that it's actually meant to be used is you tell it the x and the y range. So this is going over the 0 to 1 range on x and the 0 to 1 range on y, which is telling you the debugging range, and it's showing you that parameter. And it actually gives you out x to use as the input to f of x. Oh, that's weird.
No, I think you have to go the other way.
No, it's that didn't used to be a requirement. So this is actually, it looks wrong, but we're actually feeding in the output of this function into itself, but it's actually separate paths inside of the material function.
Okay.
But that just gives you a useful way to have a guaranteed x that matches up with the mapping of the UV chart. But you can also, here I have this other function, remap UV to range. We're using the same range input for both of these. So that's why I can use the x from here just to simplify the node graph. So I'm going to go ahead and do that. So just to show kind of what this does, if I were to put a power of x, we're just going to get a little nonlinear curve. If it's 1, it's going to be linear. You know, if it's 2, it's going to be doing that. If it's less than 1, it's going to be kind of a pillow curve. So this just gives us the ability to kind of debug a certain slice of a function. And it can be really, really useful when you're not sure why something is a certain way. So when we're talking about those metaballs with the smooth min operation, we can think about the individual spheres as nothing but linear gradients. And it doesn't matter if we think about those in 1 or 2 dimensions or 3 dimensions, really. So for now, we're just going to think about a gradient in 1 dimension. So let's say we have this gradient, just the linear gradient, and we also have the inverse gradient. So the inverse gradient is, of course, just going to flip it. That's what you do when you do 1 minus on a linear gradient. You've literally flipped it, and it intersects at 0.5. And if we want to pretend that those were the intersection of 2 spheres, for example, we could take this x and the 1 minus x and get the min of that, hook it up, and now notice we have a little pyramid shape. And just so to keep things kind of in the custom node family here, I'm going to go ahead and just type this out as HLSL code. So if you're just doing a single line, what's called a intrinsic function, you can just type it out without using the return node at all, or return word. You can just say min a, b, and end in a semicolon. And then, so this is the shader debug. Notice it's saying undeclared identifier A. That's not the most useful debug, since that one would have told you anyways. But it's because we typed a variable in our shader that we're not hooking up. So we're going to type A and B now. So we have our A and our B in the unnecessary third parameter, which I guess...
It comes with one, but it always comes collapsed.
That's all right.
I always forget about that.
Move this over a little bit. So just wanted to show that it doesn't matter whether you do this with a... Of course, something matters. What's wrong? Oh, it's... The argument type needs to match what you're returning. So I'm returning a float, so I need to make sure that the output type on the node is also a float rather than a float3. So you see here, I basically delete that, and we can even call this min. So now we have created something that's basically identical to the code min. You can't really tell them apart.
This is a good way to make sure that what you're actually doing is mathematically correct. It'd be the same as if you were trying to do the inverse of something, and then you went into Photoshop and you inversed the color, then you checked what that color was back inside of Unreal to make sure that you're getting the same results. You always want to proof your work in another way just to make sure your math is right.
Right. And we wouldn't really ever use this for such a simple case as just the min, but just as a starting point so you guys know, this is basically what you would get if you had two distance fielded spheres and you used a min operator. You would get a hard line intersection without any sort of smooth blend.
Oh, so we wouldn't get the balls that look like they're like stretching out to meet the other one. It would just be, it grabs it.
Exactly.
There's no stretchiness.
So I'll show you guys how to do that real quick. So if you think about conceptually what needs to happen, we have two gradients going the opposite direction and we have them meeting at the middle. The point where they meet in the middle is where they intersect, and by definition that's where the value equals 0. So we could of course check that by just taking the absolute value of the min, or sorry, not the min, we would take the difference. So we're going to take one of those fields and subtract the other, and then we're going to get the absolute value of that just to debug it. And you see that is showing you the difference starts at 0.5 and it creates a gradient in either direction. So using that information of the difference point, we can kind of crossfade between the two in a way that is smooth. So let's see, we've got that. So I've got some of this code down over here. The next step, we divide by that value k that we were talking about, which is for this, how wide the smooth between the points is. We'll just keep that at 0.5 right now. And then the next thing, we'll notice that just kind of rescaled that a little bit, but it's still centered at 0.5. What we really want to do here is biscale this so that if we had a linear gradient, we want to get that linear gradient back going from left to right. So it doesn't look very interesting in this case, but now we have a gradient that matches across the two, and as we increase the sharpness of this, you see it still stays centered. And we're going to actually, in this point, use that as the alpha to lerp. Oh, actually, we need to clamp it first. Not in this case, but to be correct, we do. So next we're going to lerp between, this is our A, and 1 minus was our B. And this is not complete yet, but it's going to be a lot closer than what we were seeing before. So notice now we have kind of a smooth blend between our A and our B.
Parabola?
It looks a little different than our minimum. It kind of went out of bounds a little bit. You see, it's got the shape. That's because it's fading a little bit too far. It kind of overshoots if you think about it that way. And if we start to make our pinch smaller, you see we actually have a bit of a problem with that overshooting. Now, if we think about how to solve that overshooting problem, this value here is basically a 0 to 1 gradient across our intersection point. If we multiply it by its inverse, 1 minus, so we multiply it by its inverse, we're building out something to take out that overcorrection.
Oh, okay.
So you notice if we just if we don't multiply by its inverse, each one of these is a gradient that's kind of going the opposite direction. So that gives you a nice little round shape when you multiply them together. And then finally you multiply it by that width modification that you made and subtracting it from. So to show the effect of this subtract, here's our smooth min now. Notice it's got that little hump. We're going to subtract out this little bit here and it should be perfect.
Oh, cool.
So now, sadly this isn't a material instance so I can't scrub it, but I think you guys get the idea that it never overshoots either distance field and it stays smooth. And now we did that, I honestly did this when I first was messing with this just to validate in my own head the understanding of how this math works. And I'll give you guys a good resource. There's a website by a guy named Inigo Quiles that I'm sure a lot of you have already seen that is a great resource on this type of math, but you can use this type of workflow here to validate it, and sometimes you can figure out your own modifications to it. So we could take this that we've done here and convert it into the custom node. I've already done that and just put it aside. And I guess I can kind of step through it while looking at the nodes to kind of show you guys that it's the same. So here, this first line, float diff equals a minus b over k. That's basically the same as these nodes here. We have, that's the a minus b, and this is dividing by k. And then the second line is the biscale, which say you have a gradient going from -1 to 1. When you add 1, now it's going from 0 to 2. You multiply it times 0.5, now it's going from 0 to 1. So this is a standard constant by a scale operation. And saturate is the simple way to clamp something from 0 to 1 in HLSL.
Yeah,
you'll learn to love it.
Don't look up the word clamp. The word you want is saturate.
Yeah, I mean, you can use a clamp, and there's times where you want it because it gives you control, but typing out a clamp is a huge pain.
It's a lot
Saturate
of
is
stuff
super
you have to
convenient.
build in, or a lot of fields you have to fill in for a clamp.
Now we are up to this line right here. So the next line we blend, which is simply lerping between A to B, and that's where we were at this point, lerping without the correction. So the final step is, of course, to subtract out that difference. So we have blend minus equals the difference times the its inverse times that width ratio, and you return that. So I'm going to go ahead and copy this, and I'm going to paste this in here after I make a pin for K, because I don't want to see that warning again. And I already have this guy. I'm going to go ahead and type them over. So now paste that, and it should, with any luck, look the same. All right. Yeah. So all of that is kind of a long way to say that this is kind of how you can model and create functions between HLSL and nodes and make sure that they're working correct. And this can be reduced down to further as well. But that was just for simplicity. I wanted to have a line for each major step of these guys. Yeah,
and as you can see, he did exactly the same thing in the HLSL code that he did with the material nodes, but the material nodes are going to run faster because when the compiler goes to look at everything, you can close that one down. Okay. When the shader compiler goes to look at everything, it's going to start folding parameters together to optimize, and it does that all behind the scenes. You have no control over what it does there. But again, it's a perfect example of he made something in HLSL but can do the exact same thing in the nodes.
So here's a great resource that people should probably find and bookmark. It's the Microsoft Intrinsic Functions for HLSL page. And this is another great example of things you can sometimes do in the custom node that you can't yet do that are not exposed. For example, if you want to do a tan 2 converting a vector to a angle, you'll use the custom node. You can pretty much do almost every function in here. There may be a couple that are not usable because the engine has different macros for them. For example, if you try to use lowercase ddx, it won't work. I believe you need to use an uppercase ddx. ddx fine will not work, but you shouldn't try to use it because it's very slow. But for example, most operations like a absolute value, a cosine,
dot product,
these are all pretty simple. And this page is great if you think you saw some function and you want to look through it. A lerp, where is it? So, and if you click on it, you want to see what does it actually expect. It tells you it takes x, y, and alpha. So I find myself doubting things like that again. Often I'm like, is it the alpha the end or the beginning? So you go to the page like this for reference for that. So the next thing I wanted to mention was how to find what you need to use. And that kind of comes down to, sometimes you want to find something that's not exposed, or you want to do your own modification to something in one of the, using some of the view parameters. Go ahead and start with that first case. So as we said earlier in the disclaimer, usually you want to use nodes, and even when you're using the custom node, that applies. And what I mean by that is you can access a lot of parameters. For example, I could type in here parameters dot absolute world position, and that would give me the world position inside of the custom node. However, I usually suggest, if you were to do something like that, that instead you actually place down the world position node and then hook it up into your custom node, and then, you know, give it some simple world pause, for example, and then, you know, just in here, if you need, you just start using that instead. And the reason why that's safer than typing out what the code name for world position is because the buffers in the code are subject to change. We just actually had a case of that a little bit ago for 4.11 for the instance stereo. A lot of things that were previously on the view uniform buffer were moved to different places, like the frame buffer. And that's just because for the instance stereo, there's a lot of parameters that need to be different for the left and right eye, but there's some that don't need to be different, so they split certain ones up to avoid having to split everything. And so basically you could write some code that works fine now, and it could break in the next build because view dot or view dot camera world origin is now frame dot camera world origin. You know, something minor like that. Whereas if you use the node, that gets fixed up in code using the GUIDs, so it's more safe. But you know, there are still times where you can't do that. For example, if I wanted to do distance to near surface, which is for distance fields, if I want to sample this from a single position, I could, you know, sample from the world position, and then I could hook this up here. But what I couldn't do with this state is I couldn't resample this distance with my own variable. So when it comes to things like that, you actually do need to call the function inside of your custom node to be able to control it inside of your loop. And if you're like me, you probably often are not sure where to start looking to find out how to access the code of a node. Or even if you do know how, you realize it's daunting and you have to dig through too many files. So a little trick you can use is just hook anything up to emissive, go to HLSL code here. We're going to go ahead and copy it to, I'm going to make it WordPad doc. Is there no word, anything?
You're missing the R.
Oh,
there you go.
Yeah, keyboard's a little loose. Sure. All right, so I just pasted in the hull shader for that material. Notice it's really long, and we only really care about one thing. I'm just going to search for get emissive raw, because that's where I hooked it up. Is this not a search thing? I think it's only searching before. Oh, there we go. All right, so, and just to point out how that came about, this is an unlit shader. I hooked it up just to emissive. The shader is still going to write out inputs for all these inputs and include a bunch of common template code. So that's why this file is so long, even though all we did is literally this right here. So we search for a get material emissive raw, and that points us to here. And you can actually see how the engine sampled that. So you can see here it defined a local, and it used get distance to nearest surface global. And what that does is it actually looks up the globally combined distance fields, which use clip maps similar to cascade shadow maps, and it returns the minimum distance at that point. And it's using this code here, get world position underscore parameters. And in the past, that changed recently as well. That used to just be material parameters dot absolute world position. So that's another case why it's nice to use the nodes. But we could then pull this straight out of here and type it into a node, for example, and it wouldn't really matter. So we could, actually this project doesn't really have too many distance field things in it, so I don't really think there'll be much to show with it, but I could try real quick. Let's say if I just hook that up, obviously it's going to mess with our debug shader. So the reason it's black is probably because it's actually affecting distance fields right now. There we go. So, that's not right. Something weird is going on here. I'm not sure what's going on with that pyramid, but the node is actually working. We just need to divide by something, I bet. So, it's most likely not liking the huge values. Let's say if we do a divide by 1,000 and a clamp.
Always running out of screen space.
Yeah, these...
Story of my life.
So I just want to make sure this works here. We need to get a new mouse over here. There we go. So I don't know what's up with the one on the left. It shouldn't be affecting itself, but you can see that now we're sampling the distance to near surface. So as we move this cube, the other one gets darker, kind of as we'd expect. Alright, so I guess we show a little bit more about the metaball material.
Let's jump some more into the metaballs.
Add some features to it now that we kind of showed how that smooth min was working. So you'll notice here I mentioned that we're doing the second function. Notice what we have to do here is all of the parameters that this second function uses, they have to exist in both functions right now, just the way that this is. So we have, for example, k, sphere, and t, they all just have dummy variables hooked up. And it's important that the type that's hooked up to here is the type of variable that you want this to create, because the engine actually writes the first line of your function, which initializes the, declares the inputs and things like that. So by the fact that this is a v4 makes these float 4, the fact that that's float makes these, and float 3, etc. So you see here, and this is actually doing 3 different distances. Why don't I just put that into Notepad real quick? Do this one. Alright, so this is the evaluate the distance function. These are simple sphere distance functions, distance fields. It is the distance between the world position and the sphere position minus the radius. And we pack the radius into the alpha channel of the v4 just for convenience here. So we have 3 different distance fields. If we just were to take the min, it would all look like, I actually don't have any mins right in here. We're taking 2 smooth mins. So if I could replace these lines right here, these last smooth min lines, let me go ahead and do this. I'm going to make a simple copy of this. So I'm going to get rid of that, and I'm going to say S1 equals min S1, S2, S3 equals min S1, S2, S3, there we go. And then we could just say return S3. And also I'm going to remove this. This stuff right here is just extra junk to make ripples in the main metaball.
You said return S3, but you typed 2.
Oh, good catch. So this is basically the simple evaluate distance fields. It's just giving 3 fields, and it's giving the min between all of them. And you see if I do this, it should just get rid of that smooth operator with any luck. So notice now, even if our spheres get close together from the view, they're not going to converge. I went the wrong way. There we go. So now we have a hard edge because we're not doing that smooth min. So that smooth min was basically a version of this code right here, just a little bit simplified down. And for more information on different distance field blending operations, I suggest checking out this website, Inigo Quiles. He's got a lot of cool little bits on distance field things under articles. So definitely a good resource. Alright, so that shows the min, and now there's some other features in here. Right now, this is basically just doing the simplest of traces. All it's doing is checking to see if it's visible or not. So, let me jump up. We're doing this version here. What we're basically doing here is we initialize a counter at 0, we go through the steps, we check our distance field, which basically gets the minimum between all of our 3 spheres. It's basically saying which one is closest. And then, if our current step is within our threshold, we're going to return 1. And if it doesn't happen, we're going to return 0. So this is just returning 1 or 0. And then at the end of each step, if it didn't return anything, it's just advancing the ray by the distance field sample. And it's also using a min step size just to keep it from taking really tiny steps at the edge of something, which tends to happen with distance fields. And then it also increases the min step size over time. So this is basically just a way to say, march from the camera towards whatever, and if I hit something, return 1. If not, return 0. So it's a pretty simple shader. It looks a bit long because we have to duplicate all of these inputs, like sphere 1, 2, 3, in both places.
Now, could you duplicate them in both places, but then use the same parameter, or do you need to use separate parameters for everything?
Okay, so it doesn't really matter what I hook in to this node over here in terms of what the values are. It just matters what type of variable it was, v4, v3, because these are not ever going to be called. In fact, they
just need to be initialized, or the compiler isn't going to know.
Exactly. In fact, this version of this custom hookup in here isn't going to be used at all. That's just putting it in there for the compiler.
Okay.
So for example, if we wanted to go and verify that, we'd just go HLSL code, copy, do our same trick, and I'll search for something like, oh, it's already custom expression 0. So, oop, I moved, of course. That was right there. No matches found. Not the most useful search I'm finding. Alright, no matches.
What?
Let's try that again. Now
Yeah,
I find,
okay.
So notice we have custom expression 0, evaluate the distance. Blah blah blah. And then custom expression 1 is our full function. So notice here it declared this material float custom 0, but this doesn't actually get used. That just forced it to put it first in the shader. The only time it's actually used is when it's called from here. So we're actually only passing the inputs from the main node, which then get called in return for the second node. So you see that's all the custom nodes. It also, for some reason, duplicates them. I don't know why it doesn't use them. So
just to make sure it has them.
I don't know why there's 2 copies. That's not too important, but okay. So next I'm going to, rather than it just being an on or off, I'm going to add the ability for it to get a density. So for that, we're just going to replace the inner part of this loop. Right now it's if we get inside of a surface, we return 1. If instead of that, we do a second trace from that point, which is basically a secondary counter, 16 steps, same story, except this time we are doing, instead of using the distance field to decide how far we push our array, we're using a constant step distance. And the reason for that is because for shadowing, something like subsurface, you're not just trying to quickly find the intersection of the surface. That's not that interesting to you. You want to figure out how thick of surface existed up to a certain point. And usually that distance is basically your maximum opacity distance, such that when you trace through it, it wouldn't matter, so you can just quit and say full opacity. So
you could basically give yourself a stopping point.
Exactly.
If you wanted to.
And you'll notice normally I would have a higher max steps than 16, that's why we see the edges. So I'm just going to select this return float 4 and paste that additional code in. With any luck, it's just going to work. Alright, cool. So now we need to adjust our... So notice we have the alpha and the RGB. That's because we packed 2 different things into our return. I'll go over that real quick. So right here we are returning a float 4. The first 3 things is the normal, which we haven't calculated yet. It's simply using this empty undeclared normal here, just to keep this shader so I didn't have to change too much each time I modified it. And then it's returning a cum as the alpha instead of 1. And a cum is basically, anytime while it's marching through this distance field, if it's within its threshold, it accumulates that amount that it's within the threshold. So it's kind of like, say I'm tracing through a cloud. Every time I'm within the cloud, I add that cloud thickness to the density at that point. So if we then look at the density in the emissive, using a density function, I'll have to tweak the value so that it shows up nicely, but give it a sec to compile.
Is it assigned? I don't think it's assigned.
No, it is.
Never mind.
I just need to adjust this parameter. There we go.
Oh,
so this is basically, I'm visualizing the density through the distance field right now. Actually, you know what? I'm going to go ahead and increase the step count right now, because that's bugging me. So this 16, which this is actually, we used only 16 steps total for the ProtoStar version. That one is actually rewritten entirely to be, the first ray trace was done in the Vertex shader using real geometry, and then only a few steps were taken in the pixel shader for the refraction. Alright, so now we are looking at the density with more steps, and you can see it's a little bit nicer. And we can adjust that density, and it's going to change the appearance of how thick these guys are. So, there we go, something like that. And what this is doing here is this is using the function exponential density, which you can also find some stuff about that on the Microsoft site as well. It's a very standard formula, which is basically exp to the negative e times d, which is our density. And our density here is pretty much a scalar. And it basically remaps a linear curve to an exponential curve. It is very similar to what you'd get in real life with that. So now we have the density. What if we wanted to then get a normal as well? So I'm going to go back to the Metaballs code I've got over here. So to get the normal, all I have to do is add these few lines just before that extra loop I just added. And what that, I'll do it here. Trying to think, yeah, I think I should go before. Yeah, so what that does is once it's reached the threshold, it makes one more quick correction using the last sample just to reduce the precision artifacts when using low steps, and then it creates a normal map by taking 3 samples. So we have a sample offset X, Y, and Z, like I mentioned before. And I have this parameter O here, just as a tweakable parameter, and that's actually another one of the things making this look big over here. This value, normal sample offset. And the reason that was made tweakable is because normally the more correct way of doing a distance field gradient is to actually take 6 samples. So you do positive and negative X, positive and negative Y, positive, negative Z, and that reduces any biasing. So right now when we're taking a sample basically up to the right, it's sort of going to it's going to skew the normal a little bit to the up and the left, especially when you have things like intersections and corners. But for the mobile demo, obviously I was trying to keep it cheap, so I only did 3 samples. And then, so it actually is able to bend the tracing vector towards the detected normal using the refraction parameter. And that does something interesting, you'll see in a second, where it'll actually change the appearance of that cloud inside of the shader. Of course, assuming I paste this into the right spot. Okay, here we go. Should still compile, should look the same. Good. Okay, so now not only do we have a normal, but we have a refraction parameter. So I'm going to do the refraction first, since it's on the left. Right now it's set to 0, so it's not modifying anything. Come on now.
There we go.
So, and here's where I'll usually start disabling the speed, because I really want to see this in an exact spot. And this is why I have the start offset. So, because I might want to see what's my maximum shadow accumulation. Right now I can tell I'm not really accumulating past that maximum distance there, you can see, because it's not getting any darker. But this will give us a good view to change the refraction parameters. Alright. So you can see that when I change the refraction, that's actually this sphere mesh, it gives you this interesting look where as things are moving, it's not just a linear, you don't see exactly what's behind it, you see the refracted information. So you see it's this cool magnifying glass kind of thing. And that's without doing any normals or anything. So we have the normal here on the RGB. We haven't used it yet though. So if I wanted to add a reflection here, and this is something to point out, is in the Metaballs for the Ronin demo, or sorry, the ProtoStar, was actually just a completely unlit emissive material. It was masked, and all of the reflections and things were just done with cube maps of the environment. So you see here I have a cube map of the sky, and I'm going to take the normal and do custom reflection vector, and then use that as that. And I'm going to just, I guess the correct thing here would be to use a Fresnel or something like that. Sure, multiply it by a Fresnel. I can't remember if it needs to be inverted or not, but we'll find out. And then we're going to just add it to our emissive. And I'm also going to darken down this, this exponential density a little bit so it doesn't look so bright. There we go. So just wanted it to be a little bit darker so that we can see the cube map reflection on that. Whenever it compiles, of course.
Wait for it.
No rush, editor. So now we've got the accumulation plus we've got that little bit of reflection.
Really cool.
Excuse me. Plus that magnification going on. So one of the things that's affecting how soft the shadows look here is you'll notice that in the tracer I had this, for the shadows, I have this, instead of checking the same threshold that I was checking up here for detecting the actual surface, when I'm detecting the shadow, I'm a little bit fuzzier with that check and I give it an extra spread. So you can see if we had the shadow mode at low, you get a very crisp, sharp look at the shapes.
Okay.
As you increase that, it's actually saying that there's more density surrounding the spheres, so I'd actually have to counterbalance it by reducing this. So basically I just made the shadows much softer. Notice that they're affecting from farther away,
Yeah.
and it makes it look just kind of more glassy. That's just, these are not completely correct ways of ray tracing. There's better ways. Don't take this as a ray tracing or ray marching Bible by any means. These are just some hand-placed hacks to make things look cool. But that basically gives you most of the features that were actually inside of the Metaballs that we shipped. It had a little bit of extra things going on, like it actually had a second refraction hit as it exited the surface. And I'm actually going to go and jump and show that actual version of the material, just so you can kind of see what is the kind of end result of something like that. So we've got different versions here, and notice we can kind of move around and we see the scene, kind of different levels of refraction, and it matches the background colors. And this is a blueprint here, so we can actually scrub it, modify a lot of things, such as the spacing between them, how many groups of 4 there are, and it kind of automatically keeps doing this. And so we've got different different materials for different looks, just changing those different things like different refraction properties. So you see when I change the the material, we get a lot of different types of looks. Give me 1 second here. Oh. Some of these have bad settings, that's why we're seeing these artifacts. But you also get this kind of very cool soft look with some of them as well. Let me see, probably not that one. Different cube maps. So it's this kind of very anisotropic look that makes it kind of feel cool that we went with in the demo. So I'll show the shader for this briefly, but it's a mess because, like I said, it was totally taken apart to be optimized for the phone. And it's quite a bit bigger than what we were just looking at. So all the extra stuff added. The main change, though, is that this is done on the Vertex shader rather than the pixel shader for the first trace. So in notice, one of the biggest things to make this run faster, if I go to shader complexity, notice here that these are actually using a real geometry, maybe a few units wider than the actual balls. And that makes it so that the ray starts much closer to the surface and it doesn't have to seek to find it. So I actually do that trace in the Vertex shader. And it's actually a much simpler part of the code is the Vertex shader trace. So this is actually the ray march for the Vertex shader. Let me go ahead and pull that into a notepad. Excuse me. So this looks big, but it's basically, I wanted this code to compile faster, so I didn't use a loop. I only do 3 steps and just do them. So it's getting the distance field, move the point, it's get the distance field value, accumulate, do the, adjust the point, and it adjusts closer and closer each time. So and then it returns how much it had to move those verts, basically. And then that gives the See, that goes over into the vertex shader here, the world position offset, all the way over there. So that starts there, and then we also generate the normals using the yeah, actually I ended up using, to get this on the vertex shader, I forgot about this. Because I mentioned earlier how the engine is copying some of the functions like 1s and 2s, and because some of the functions were on both the pixel shader and the vertex shader, I was having trouble reliably calling the same function in the vertex shader and the pixel shader because it kept reordering. So I ended up redoing that whole distance field gradient math using a material function. So this is pretty much the exact same thing that you saw before. It looks messy, but it's just getting the distance field using the material, and that was just a necessity to get it. At the end of the day, one day it was not compiling, so I just decided just to do it that way. So, and also we do a couple other things, like notice just passing in time, whereas before we were doing it literally passing in time. Here we'll use the custom UVs because it makes a difference for mobile. Where are the custom UVs?
Oh, way down there.
Yeah, way over here. So, let's see. That's custom UV 0, here it is. So, and then the append, here it is. So, I'm doing this time in the vertex shader, and that was important because on mobile you're in lower precision, and if you don't do your time in the vertex shader and pass it over, you'll get horrible stepping artifacts because time loses precision. And basically the ripples started looking like they were at a lower frame rate even though it was running fast. So that's just something to keep in mind if you do stuff like this on the, you sometimes have to jump through hoops to pass things through the vertex shader, and it might make it look a little bit more confusing. And then also this evaluate distance field, I had this twice as well because of that same limitation. It made a different version of the function for the vertex shader, so just having them be separate made it easier to call between them without any compile errors. And so the rest of this stuff is just doing the refraction and doing the textures and things like that, but I guess I can mess with some of the knobs on one of these instances. Let's see here. Oop, wrong shader. For example, the effects of the certain refraction values. Right now we have a refraction value of 0.5. With this setting here, we're almost looking at the backside normal that the tracer detected, which is used to kind of lerp between different values. And you see that we actually are running out of our trace distance over here, which is why you see that kind of artifact. But in motion, you didn't really notice things like that. But and then if we change the internal refraction, if we set that to 0, what we actually see now, we're actually seeing through like it's completely translucent. You see that? It's not doing anything. So just as a test, sometimes you only need a little bit, but you can also do crazy things like make, you wouldn't really want to do this, but you could make the refraction super exaggerated to give you a crazy artistic feeling if you wanted to. But yeah, so these were not physically based reflections or refractions, although I did do a little bit of research on that using Snell's law, but it turns out that and doesn't always look as cool as sometimes hand tweaked things, especially when you're talking about just a little tech demo shader. And also doing the correct Snell's law requires more cosine math. It's more expensive than the simple lerps that we're doing here. I think I got through most of the stuff except for talking about alternative uses of the custom node, like accessing things deep within the engine. So a good resource for that is, here we go. There's this documentation page here called the FFU Uniform Shader Parameters, and this is basically where you'll find everything that's used under the hood in the engine, and you can access it using the custom node. And this is just to give you guys an idea of what the view parameters are. So the engine takes a lot of input from you when it renders a scene. You have different post-process volumes, you have different camera settings, you've got different everything. There has to be a central location for the engine to agree, okay, this is what we're actually rendering. The uniform buffer is a place where all those settings exist. So even though you have infinite post-process volumes that blend, you actually only have one set of settings where that actually gets bound to. In things like distance, depth of field, region, length, you can get all of that stuff. So for example, exposure scale. What if you wanted to get exposure scale? I'm sure there might be a node for it. Let's make a new material here. Instead over here is empty. Call this debug. Alright, so do custom, and then we're just going to say view dot, and what was the name of that again? Totally. Exposure scale. Of course, thank you.
Yes, there's an error with your
shader. It
shader.
compiled that I didn't have anything typed. So now, another useful debugging option is these debug nodes. So debug scalar parameter here. It's giving me an error because I didn't make it float 1. So this is actually telling us our exposure scale right now is at 1, for whatever that means. I'm not sure if it is this exposure that it is using. We probably have to put it on a scene to, let's go back to a blank map. Just give us a
One
test map.
second.
And then put this material on it. There we go.
Our exposure is 0.98.
So I'm not sure if that's going to be affected by this. Oh, it is. Okay, cool. So we're accessing our exposure now directly with that. When it's at 1, obviously. So that, once again, is literally just having view.exposure scale. And there's a lot of other things you can get. Usually what I've seen people doing is getting things like depth of field. But there's also, you might want to get the near plane or something like that. Or you might want to get the clip to world transform. For example, if you want to convert between depth and world positions and things like that. So you could do things like find out how much the camera had moved by using these previous preview translation and preview translation, and you can see how much the camera had moved. In fact, I had to do that recently for the McLaren demo for a car paint shader. We had sparkles that they were actually looking too strong when the camera was stationary and not strong enough when the camera was moving because of the way temporal AA worked. And that it only happened when the camera was moving, not when the camera was panning, or when the camera was rotating. So using that, I was able to figure out when the camera was above a certain speed and increase the amount of the sparkles a little bit. Or actually, I was doing the opposite, darkening them when the camera was stationary. Just to kind of fine-tune and remove some of the artifacts, because something like temporal AA has a hard time with noisy content, because fundamentally it's trying to find noise and remove it. And when you make a shader like car paint that is purposefully injecting a lot of noise into the engine, the temporal AA shader kind of freaks out. So sometimes we would call them hacks for sure, rely on hacks like that to reduce, any artifacts that ruin the immersion for people. And, for me, I'm the type of person that says, whatever works, fake it till you make it. I have no problem with hacks. The games are built on hacks. And sometimes people who look down on hacks are not making as many things as people who do hacks. Whatever, gets it done, as long as you make sure that it's testable and people know what you're doing, obviously.
And it's performant. It doesn't matter if it's a hack. Just as long as it runs at the acceptable frame rate, then you found a great workaround. And
before you do too much, grabbing stuff from the view buffer, you might want to check with your project rendering programmer and just let them know, because they might tell you, oh crap, I'm about to submit a change list tomorrow that renames all that stuff. Or they might tell you that's not a good idea because we're doing X. So just be advised on that.
Yeah, whenever you're doing something with the custom node, again, this is for that 0.0001% of the time where there's something that you can't do. You're going to want to talk with somebody on your engineering team who's either covering rendering or one of your other programmers, just to make sure that you're not doing something that goes against something that they've either injected into the engine themselves or that's completely out of your platform's capability.
So another useful thing you might want to do is do a transform inside of here, and you can do that using the matrix multiplies, which is just mul and then view dot, view to translated world, and then view to translated world, and then our parameter, what do we call it, A, and of course we want it to be a float 3. weird.
Did it not make?
It didn't make the input. Let's try that again. And I'm also, did I get rid of, oh, I did this. My fault.
Ah.
I'll do that in Notepad because typing in there is a view to translated world, so I want to do mole. And I can't remember, sometimes the vector needs to go first. I can't remember. We'll find out pretty quickly. So let's say we wanted to do, transform something to view space. You might do that in a node sometimes for whatever reason. And then I'm going to use the debug float 3 instead of debug scalar. I'm going to see. So yeah, that is working. And then okay, so 0, 0. That's weird. It's not. Well, I'm not 100% sure what this matrix is actually returning here. Let's make this a vector parameter. It might be that it doesn't translate that point. There we go. So in this case, it's transforming that from view space to world space. In case you want to do matrix math, that's a quick way. And then here's a fun little bit. Sometimes I use custom nodes for prototyping code that it may not even end up as shader code. Like this was a shader for converting height fields into distance fields, which was the first step in an alternate version of parallax occlusion mapping that I was working on a few months ago. And the ideal way to write this is actually in C++, because to generate a distance field texture, you iterate over quite a few texels, almost all of the neighbors.
Yeah, we were talking about the math of this. You have it clamped at, what, 256?
Yeah, right now,
anything higher would result in, I think you said it like, what was it, 512 would be 1,000,000 pixels per, or 1,000,000 samples per pixel or something like that?
Yeah, something like that. So this is doing a nested loop. It's basically looking over our height field texture, and from any given UV pixel, it does a search based on the height that you tell it that height map is around, and it returns the nearest pixel that it found to that spot at the top of the height field volume. So to do that properly, I actually needed to end up doing it in code, because you can crash your GPU if you try to do this in real time on a high resolution texture. But just because it's so much easier to write code in HLSL compared to C++ when you're doing texture modifications, this was kind of invaluable, because it only took me maybe 20-30 minutes to write this in HLSL code, whereas it took me a whole day to convert this into C++, because you can't just nicely sample a texture and have an implicit for loop, where in a material function we're already kind of, or in a material, whenever you access a texture from a UV point, you're already in an implicit for loop where it's doing that for every pixel, and you have that. In code, you have to literally go through each pixel by hand and do that as memory pointers, so it can be more work. So starting out in here for simple things is nice. So you can see here I'm changing how tall the distance field is, so you can see it searches more to the side. But you can see we're actually starting to kill the performance a little bit, and this is only a 512 by 512 texture. And yeah, I'm clamping it at a certain radius. So notice if I do this, how much I just killed the editor performance. So that's why sometimes you can prototype things in here that you know you're not ever going to use, but it's still convenient.
Oh, and the prototyping brings up another good point. So say Ryan was building this, and he's like, okay, I've got this, it's good to go, but I want to use this for X, Y, and Z in my project. What you'd want to do then is take that over to an engineer or somebody on the programming team and have them convert this into C++ code. That way it will run as quick as possible, and you can get it as a very, very quick built-in shader editor node that you can just drop into your graph at any time. So it's, again, that's one of the ways that you can get around having something that's very non-performant in terms of being in the custom node, and then turn that into something that is actually performant and will run on a multitude of different platforms. That's kind of how you get around those types of limits when using this particular node to make sure that it is going to run and is going to run at frame rate. Because that's the most important thing. No one can play your game if it doesn't run at frame rate.
So just real quick on the thing that I did for limiting crashes in this shader. So this is a shader that looks at the texture. It gets the dimensions using this get dimensions lookup and fills out the size and everything. and then I'm actually clamping the texture size to be the smallest of either the actual texture size or 256 times my scalar, which is defined over here. And that's basically saying never search more than a 256 radius, which is a pretty big radius. Hang on a second, let me double check the math. I'm not sure if it's actually doing in each direction. So it goes to, so if your height field was 1, it could go all the way up to 256 times, so 65,000, yeah. So yeah, that's going pretty bad, which is why we started to see it slow down a little bit.
And that's 65,000 for each pixel that we're rendering. That's a lot.
So
and you see 256 texel texture.
This is a standard nested loop again for something like blurring or anytime you want to research a radius. What we do here is we have an integer, and we start it at the negative search length, and we check until it reaches the positive search length, and then we just increment it each step. And same thing for the y-axis. So, and then of course we initialize a sample position as the starting UV plus, to get our 2D position that we're looking up, we simply divide the space, the coordinate of our loops by the texture size, and that just brings them, instead of being in 0 to 1 of the texture size, it or sorry, rather than being in pixels, it brings it in 0 to 1, which is in UV space. And then it does a sample the texture, and then this sample Z is a way to invert, because of the way I was handling inverted opacities. And then this is just the min dist that's tracking the current sample distance, and then checking the previous minimum distance as well. So that's pretty much how that works. It's just a neat little thing you guys can do, and maybe if people want to see this stuff, we can make these different shaders available.
Yeah, that's actually one of the questions that we have, is that we're going to make any of this available.
I think the ProtoStar demo is supposed to release at some point. I'm not sure when. I think it's going to be a little while out.
Okay.
But
so you got anything else? We got a little bit of Q&A here. So we're going to jump into some of these Q&A questions and then do a recap, and that'll be it for us for today. So the first question, what does one need to think of when using custom materials in the various platforms for PC to Linux, VR, PS4, etc.?
I mean, the more platforms you're shipping on, the more careful you have to be, the more testing you'll need to do. So
I do believe PC will accept HLSL, obviously, but PS4 looks for CG code. And again, if your code, it looks at that node and it assumes that your code is correct, so it's just going to spit that code down there. So if there's an error, or you're doing something that a CG shader doesn't support, but it does work on Windows, like that's going to be one of the things that I don't understand why this doesn't work. So you're going to have to go through, or at least keep in the front of your mind at all times, hey, I wrote something custom using the custom node. That might be the reason why it doesn't work on the PS4 or the Xbox One. I would highly recommend staying away from using the custom node if you're doing anything in VR. Because again, you need to hit that extraordinarily high frame rate to make sure that people don't get simulation sickness. So it's not to say I don't want to scare you away from using it, but I would use it as absolute bare minimum. You know, this is the absolute fallback that we're going to have in order for this to work, as I have to do this particular function, and then see if you can get a programmer to roll that into a pre-made material node for you. Anything else?
Was that it for our Q&A? Or
No, we still got some more.
I think we mostly addressed that one with the shader debug and spitting out the output. Yep. So that's the one. It will actually spit out the shader in HLSL, which is what the PS4 will use.
So someone asked if we could release a few samples of the Metaballs for examples on the forums, and we will see what we can do to address that particular one. I can't give you a definitive yes or no at this point in time. But
there's actually already an example using volume decals that somebody used, using just the existing nodes.
Yeah, no.
Search. It's a little different because with the volume decals, you're just going to get the opaque value of the surface. You can't do any of that refraction or any of that accumulation stuff, so it wouldn't be quite the same, but you could use a subsurface lighting model, I believe, and get some of the light looking stuff.
You'd have like
so
cool
that one's already up there. Search for that. Search for lava lamp in Metaballs, and you'll see some stuff.
Yeah, I think the NVIDIA GameWorks integration that you can find through the NVIDIA branch also has some of this stuff already integrated into it, and you can check that one out.
Well, the NVIDIA version is something that's totally different. That's more a game feature that is Metaballs that you can use kind of agnostically, whereas in this case, this is a hard-coded shader that just says one thing, these are the balls. You couldn't very easily extend it rather than making your own controller blueprints and that sort of thing. So the NVIDIA one is probably much more of an actual feature than what we're talking about. Okay. We're talking about kind of a shader one-off here.
Let's see. Is the custom node still only compatible with PC and not console?
No, it's compatible. It's just you're flying by the seat of your pants.
Here's my favorite question that we got. Ryan, can we persuade you to get a Twitter so that we can follow you all the awesome things that you do?
I've held out for what, 12 years now?
I held out for a ridiculously long time too until they demanded at GDC that I get a Twitter account. So
I still haven't been on Twitter yet.
I have one now, just for work stuff. Somebody wanted to see the website. We'll pull that up really quick.
Which one?
I forgot the guy's name. Yeah, with all of the distance field functions on it.
So let's see, we might still have it up. I mean, you just there
we go.
Articles. There's a lot of things that say distance field in here. It's called modeling. Distance functions. There we go. So here you go. Here is a nice place to start. This is one of the best distance field resources online for sure. You know, your basic shapes. You've got your boxes and unions. A lot of these already exist as material functions. These basic unions. A couple shapes in here exist already. We've got our boxes and our spheres and cubes. We don't have all of these other ones yet as automated ones. We have capsule. But yeah, so anything that you guys don't see, go. It's a great place to start.
One of the other questions I saw this on the forum, and it was a question about what editor do you use to write your code in? And I responded with, I use Notepad++.
Yeah, same.
You saw Ryan uses WordPad or Notepad. A lot of times this stuff is so short that you don't actually need proper syntax. If you run into a case where you're like, oh, I need proper syntax highlighting and things like that, you're doing too much inside the custom node. And take a step back and figure out where you can actually roll some of this into C++ code or where you can use this with the nodes. But for everything that I've ever used it for, I just use Notepad. Simple, quick. And let's see, is there anything else? Nope, that's it. So today we covered the custom node and how to use it. Use it only when you make something that can be made with the in-editor meshes. And we got to check out some amazingly cool metaballs and learned a little bit about distance fields and how we can use those to make ridiculously interesting effects and shapes, such as the metaballs. Is there anything else you'd like to add?
No, I mean, I think we covered a lot. I don't know, do we have a chat log? Is that where those questions are
coming
from?
Yeah, that's where the questions
as long as we've answered everyone's questions.
We've answered all the questions. So, well, that's it for us today then, guys. We're going to go ahead and knock it on the head here. If you have any more other questions or anything like that, respond to the forums. You know, I check them every day. I know Ryan checks them every day. And we will do our best to get back to you with any questions that you have, and we'll look into releasing some of this stuff as material functions or something like that when we get the time. So thanks everybody for tuning in, and we will see you guys next time.
Thanks.
See ya.